Akash. I am Meghraj.
My name is Yuvraj.
My name is Sakshan.
Hello, I am Tarun. Electric motors can be of two types on the basis of magnets we use. One that uses permanent magnets and another one that uses electromagnets. Next one. Electric motors with that uses permanent magnets. In these motors, one of the stator or the rotor is made of a permanent magnet and another one is electromagnets. The permanent magnets are generally made of rare earth metals. Rare earth metals are lanthanide, scandium or yttrium. Reasons why we use rare earth metals are that they provide very high strength in very less volume. They provide high torque density. If we don't use reasons to use rare earth metals is that they provide very high magnetic strength, very high torque density, and their temperature performance is very good. Means that they don't lose their magnetization under very high temperatures. That is very useful in electric vehicles where temperature of motor can go high. Next slide. Electric motors that don't use permanent magnets. In these motors, both stator and rotor are made up of electromagnets, but because both are made up of electromagnets, there are much more losses as compared to motors that use permanent magnets. There are copper losses in both stator and rotor but in starting से करूँगा electric motors that don't use permanent magnets. In these motors, both rotor and stator are made up of electromagnets.
जहाँ पर पिछली बार छोड़ा था ना वहाँ से शुरू करना, वहाँ से मतलब वो कोई पॉइंट हटा दे और फिर
These motors don't provide high efficiency and provide less torque as compared to the motors that use permanent magnets, because there are more losses as compared to that motors. Efficiency here decreases due to the loss here in both stator and rotors. Because we have electromagnets, these will provide less magnetic flux occupying the same volume. Means we have to make these motors big to have the same efficiency. The only problem we face while using permanent magnets is that we have to use rare earth metals for making permanent magnets, because if we don't use rare earth metals, we will get less magnetic flux torque that we can as compared to if we use rare earth magnets. But the only problem we face with the motors with permanent magnets is we have to use the rare earth metals for making permanent magnets. If we use any other, then it will not provide that much magnetic flux and torque we can get with the use of the rare earth metals. The problem with rare earth metals is that the processing is very difficult. It is not like that they are not in abundant amount in earth. They are, but their processing is difficult, and also their supply is controlled majorly by China. So we need to find the materials which we can use to replace rare earth metals in permanent magnets and still match the properties that we can get with them.
Hi, I am Akash. So when it comes to working principle of a motor, we don't have any vast impact when we don't use any rare earth metal, but I will mention them later. So in case of working principle, we have a stator, a rotor, and interaction between them. So stator, we have a rotating magnetic field, and stator has copper windings in which the AC current flows and it produces rotating magnetic field. And when it comes to rotor, we have a constant magnetic field. Like the rotor carries a permanent magnet, and here we insert that non-rare earth metal. So here one of its use comes, and these magnets provide that steady north-south magnetic field. And when it comes to interaction between them, so it produces torque. Like the rotating magnetic field of the stator pulls the rotor magnet, and the rotor aligns with the rotating magnetic field, which produces torque. And these cycles keeps continue, like the stator fields keeps rotating and the rotor keeps chasing it, so it drives the shaft continuously. So there are not too much impact when we don't use that rare earth metal on the working principle basically. But when we adjust like bigger rotor or like advanced winding or advanced control over it, we can have a great control in case of motors, in case of working principle. Now I can play the video of working principle of the motor, so you can watch it also.
In this condition, when the coil A is energized, the opposite poles of the rotor and stator are attracted to each other. As the rotor nears coil A, coil B is energized. As the rotor nears coil B, coil C is energized. After that, coil A is energized with the opposite polarity. This process is repeated and the rotor continues to rotate. Even though this motor works, it has one drawback. You can notice that at any instant only one coil is energized. The two dead coils greatly reduce the power output of the motor. Here is the trick to overcome this problem. When the rotor is in this position, along with the first coil which pulls the rotor, you can energize the coil behind it in such a way that it will push the rotor. For this instant, a same polarity current is passed through the second coil. The combined effect produces more torque and power output from the motor. The combined force also makes sure that a BLDC has a beautiful constant torque nature.
Today I will present on the current status of the magnetic technology. We will look at three important categories of permanent magnets that played a significant role before the dominance of rare earth magnets, that are ferrite magnets, Alnico magnets and bismuth. And let's begin with the ferrite or ceramic magnets. Ferrite magnets are ferrimagnetic materials, and a common example being strontium ferrite SR-Fe12O90. These are widely used in small electric motors and loudspeakers and a household product. Their key advantage is that they are cheap, corrosion resistance and have high corrosivity. However, their limitation is that they offer low magnetic strength, about 0.35 Tesla. Compared to the rare earth magnets, they are excellent for cost-effective application, but not suitable for the high performance. At Alnico magnets, before the emergence of rare earth magnets in 1970, Alnico alloys made up of aluminum, nickel, cobalt, iron and sometimes copper and titanium was considered the strongest permanent magnet. These magnets are ferromagnetic alloys and were widely used in motors, sensors and instruments. Even today, these remain relevant in the certain applications where the rare earth metal use is restricted or due to the cost or supply limitation. And finally, we have bismuth, a manganese bismuth alloy. It was developed in the 1950s and it was a rare earth free permanent magnet. Bismuth have a high corrosive force around 3650 oersteds and was mainly used in small electric motors, but eventually it was replaced by some rare earth metals because those offered much better performance at a lower cost. So while bismuth was very important historically, it's no longer dominates in today's application. So the evolution of these magnets shows how material science continues to push technology forward in motors, electronics and energy applications.
My name is Saksham Raj. My topic is challenges in current level of technology. First challenge we face is lower magnetic strength alternative of the alternators. These magnets are weaker than the rare earth metals magnets, due to which results into large, heavier motors for the same torque of the same machinery. Low efficiency and power density. Hard to reach same torque density and efficiency as rare earth metals PMSM makes them less attractive for low efficiency and density, due to which we can see that the torque density is low, which goes to the heavier EV and aerospace and make it less attractive. Temperature sensitivity. This magnet has poor performance at high temperature, and this magnet has less dimagnetization properties, under which it has opposing field.
Myself Yuvraj. I'm here to explain the future research trends of magnets. First, researchers are working on high performance ferrite magnets by using nanostructures and complete composite ferrites. Their main aim is to increase the magnetic strength at low cost. Second, by coming to Alnico, which is made of aluminum, nickel and cobalt. This mainly focuses to make them more resistant to demagnetization by using better heat treatment and grain refinement. Coming to MnBi magnets, which means manganese and bismuth magnets. These are very promising for high temperature use. However, they are still at early stage and not yet ready for large scale production. Coming to iron nitride components, these have potential for very high magnetic energy, but the challenge is to make them stable and suitable for mass production.
Finally, there are ferrite hybrid magnets. These combined ferrites with metals are additive to balance strength, cost and temperature stability. By this, I am concluding that the future magnets lies in developing materials that are stronger and more stable and cost effective. Thank you.